We tell ourselves comforting stories about the cosmos, that we live in a universe teeming with stars, galaxies, and infinite possibilities. But I'm about to shatter that illusion. The universe isn't full of stars and galaxies dancing together in cosmic harmony. It's almost completely empty, and the reason for this emptiness might be the most terrifying discovery in all of science. If you're fascinated by the cosmos and want to explore more mind-bending mysteries of our universe, subscribe to the channel and give this video a like. Your help makes all the difference. Let's get started. The numbers are staggering, and they should make your skin crawl. If you took all the matter in the observable universe, every star, every planet, every grain of cosmic dust, every atom in your body, and spread it evenly throughout space, you'd have roughly 1 hydrogen atom per cubic meter. To put this in perspective, the air you're breathing right now contains about 25 trillion molecules per cubic meter. The universe, on average, contains just 1 lonely atom in that same space. We're not talking about empty like a vacuum chamber in a laboratory. We're talking about empty like nothing you can possibly imagine. But it gets worse. Much worse. The matter we can see, stars, galaxies, planets, you and me, makes up only about 5% of everything that exists. The rest is dark matter and dark energy, mysterious substances we can't see, can't touch, and barely understand. So that 1 atom per cubic meter? That's actually the dense part of the universe. The Hubble Space Telescope has peered into what astronomers call the Hubble Deep Field, a tiny patch of sky that looks completely empty to the naked eye. When Hubble stared at this seemingly blank region for days, collecting every photon of light, it revealed thousands of galaxies. Each galaxy contains billions of stars, and this was just a tiny sliver of sky, no bigger than a grain of sand held at arm's length. Yet even with all those galaxies, all those billions of stars, space remains overwhelmingly empty. The average distance between galaxies is about 25 million light-years. That means if our Milky Way galaxy were the size of a dinner plate, the nearest large galaxy, Andromeda, would be another dinner plate sitting 20 feet away. And, in between, nothing but empty space. The European Space Agency's Planck satellite has mapped the cosmic microwave background radiation, the afterglow of the Big Bang itself. This map shows us the universe when it was only 380,000 years old, just a baby compared to its current age of 13.8 billion years. Even then, matter was distributed unevenly, with vast empty regions separated by slightly denser areas that would eventually become the cosmic web we see today. This cosmic web is perhaps the most haunting structure in the universe. Imagine a three-dimensional spiderweb stretching across billions of light-years, with galaxies strung along the filaments like dewdrops. Between these filaments lie cosmic voids, regions of space so empty they make the vacuum of space look crowded. Some of these voids are hundreds of millions of light-years across, containing almost nothing. The Boötes Void, discovered in 1981, is sometimes called the Great Nothing. It's a roughly spherical region of space 330 million light-years in diameter, containing only a handful of galaxies. If the Milky Way were located in the center of the Boötes Void, we wouldn't have discovered other galaxies until the 1960s. We would have spent most of human history believing we were alone in an empty universe. But here's where the terror really begins. This emptiness isn't random. It's not just the way things happen to turn out. The universe is empty for specific, measurable reasons that reveal something deeply unsettling about the nature of reality itself. Dark energy, the mysterious force that makes up about 68% of the universe, is actively pushing space apart. It's not just that galaxies are moving away from each other. Space itself is expanding, creating more emptiness with every passing second. The Supernova Cosmology Project and the High-Z Supernova Search Team discovered this in 1998 by studying distant supernova, and it earned them the Nobel Prize in Physics in 2011. This expansion is accelerating. The universe isn't just getting bigger, it's getting bigger faster and faster, Imagine blowing up a balloon, but instead of your breath running out, you keep blowing harder and harder. That's what's happening to space itself. Every second, the universe creates more emptiness than existed in the entire observable universe when it was 1 second old. The James Webb Space Telescope, launched in 2021, has confirmed something even more disturbing. When we look at the most distant galaxies we're seeing as they were over 13 billion years ago, they appear surprisingly mature and massive. This suggests that galaxy formation happened much faster than our models predicted, which means the universe became empty much more quickly than we thought. But the real terror lies in what this emptiness means for the future. As dark energy continues to accelerate the expansion of space, galaxies will move farther and farther apart. Eventually, they'll be so far away that their light will never reach us. The night sky will go dark, one star at a time, until future civilizations see nothing but empty blackness when they look up. This isn't science fiction. This is the measured, calculated fate of our universe, based on observations from the world's most sophisticated telescopes and instruments. In about 100 billion years, any civilization that exists will see only their own galaxy in an otherwise empty sky. They'll have no way of knowing that other galaxies ever existed. The evidence of the Big Bang, the cosmic microwave background radiation, will have been stretched to wavelengths so long they'll be undetectable. The Atacama Cosmology Telescope and the South Pole Telescope have measured tiny fluctuations in the cosmic microwave background that tell us exactly how much matter exists in the universe. The answer is terrifying in its precision: not enough. There's not enough matter to stop the expansion, not enough to bring galaxies back together, not enough to prevent the universe from becoming an infinite, cold, empty void. The mathematics of cosmic emptiness reveal something even more chilling than the vast distances between galaxies. When astronomers calculate the critical density of the universe, the exact amount of matter needed to balance gravitational attraction against cosmic expansion, they find that our universe falls short by a factor of about 20. We live in what cosmologists call an open universe, destined to expand forever into infinite emptiness. The Wilkinson Microwave Anisotropy Probe, or WMAP, spent 9 years mapping the cosmic microwave background with unprecedented precision. Its measurements confirmed that ordinary matter, the stuff that makes up stars, planets, and us, comprises only 4.9% of the universe's total energy density. Dark matter adds another 26.8%, leaving dark energy to dominate at 68.3%. These aren't rough estimates, they're measured to within a fraction of a percent. This precision is both remarkable and terrifying. We know exactly how empty the universe is, and we know exactly why it will become infinitely emptier. The Planck satellite, launched by the European Space Agency in 2009, refined these measurements even further, confirming that we live in a universe where emptiness isn't just the current state, it's the inevitable future. But the emptiness we observe today is nothing compared to what's coming. As dark energy continues to accelerate cosmic expansion, the observable universe will actually shrink. This sounds paradoxical, but it's true. The observable universe is limited by the distance light can travel since the Big Bang. As space expands faster and faster, light from distant galaxies will be stretched to longer and longer wavelengths until it becomes undetectable. The local group, our gravitational neighborhood containing the Milky Way, Andromeda, and about 50 smaller galaxies, will eventually merge into a single massive galaxy. But this cosmic collision, which I actually explored in detail in my video about how long it would take to reach Pluto, and the incredible distances involved in our own solar system, will be one of the last major events in our cosmic neighborhood. After that, we'll be alone in an expanding ocean of nothingness. Computer simulations run on the world's most powerful supercomputers show us this future with disturbing clarity. The Millennium simulation, one of the largest cosmological simulations ever performed, tracked the evolution of dark matter over the entire history of the universe. It reveals how the cosmic web formed, how galaxies clustered along filaments, and how vast voids grew larger and emptier over time. These simulations predict that in about 100 billion years, the cosmic microwave background radiation will have cooled to just above absolute zero. The universe will be so cold and empty that quantum fluctuations, tiny, random variations in energy, will become the dominant source of activity. We're talking about a universe where the most exciting events are the spontaneous appearance and disappearance of virtual particles. The Sloan Digital Sky Survey has mapped over 3 million galaxies and quasars, creating the most detailed three-dimensional map of the universe ever made. This map reveals the cosmic web in stunning detail, showing how matter is distributed along filaments separated by enormous voids. But it also shows us something unsettling. The voids are growing. As the universe expands, these empty regions don't just get bigger, they get emptier. Galaxies that were once connected by tenuous bridges of dark matter are being pulled apart. The cosmic web is literally dissolving, leaving isolated islands of matter in an ever-expanding sea of nothingness. The Hubble Space Telescope's observations of type Ia supernovae, stellar explosions that serve as cosmic distance markers, revealed that this expansion is accelerating. These supernovae appear dimmer than they should if the universe were expanding at a constant rate, indicating that space itself is stretching faster now than it was in the past. This discovery fundamentally changed our understanding of the universe's fate. But here's what makes this emptiness truly terrifying. It's not just about the future. The emptiness we see today is the result of processes that have been operating since the universe began. The cosmic voids we observe aren't empty because matter was never there. They're empty because matter was actively removed. During the first few billion years after the Big Bang, massive black holes at the centers of galaxies were much more active than they are today. These supermassive black holes, some containing billions of times the mass of our Sun, generated enormous jets of energy that heated and expelled gas from vast regions of space. The Very Large Array Radio Telescope and the Chandra X-ray Observatory have detected the remnants of these ancient outflows, showing how black holes carved out the empty spaces we see today. The feedback from these supermassive black holes didn't just heat gas, it prevented new stars from forming across enormous volumes of space. Computer models show that without this feedback, the universe would be much denser, with galaxies packed more closely together. The emptiness we observe is, in part, the result of black holes actively sterilizing vast regions of the cosmos. Recent observations from the Event Horizon Telescope, which captured the first image of a black hole's shadow in 2019, have revealed just how powerful these cosmic monsters can be. The black hole at the center of galaxy M87 shoots a jet of material over 5,000 light-years into space at nearly the speed of light. This jet carries enough energy to heat and disperse gas across volumes larger than our entire local group of galaxies. The Spitzer Space Telescope, before its retirement in 2020, detected the infrared glow of this heated gas in cosmic voids. These observations confirmed that the emptiness we see isn't truly empty. It's filled with extremely hot, thin gas that was heated by ancient black hole activity. This gas is so hot and diffuse that it's essentially invisible, creating the illusion of perfect emptiness. But the most disturbing aspect of cosmic emptiness isn't what we can see. It's what we can't see. Dark matter, which outweighs ordinary matter by a factor of 5 to 1, is completely invisible to all forms of electromagnetic radiation. We know it exists only through its gravitational effects on visible matter. The Large Hadron Collider and underground detectors like the Xenon experiment have searched for dark matter particles for decades without success. This means that most of the matter in the universe is not just invisible, it's undetectable by any technology we currently possess. We're surrounded by a vast invisible scaffolding of dark matter that shapes the structure of the cosmos, yet we can't see it, touch it, or interact with it in any way except through gravity. It's like living in a house where most of the walls are invisible. The cosmic web of dark matter, revealed through gravitational lensing observations by the Hubble Space Telescope and computer simulations, shows that even this invisible matter is distributed in a web-like structure with enormous empty regions. The dark matter voids are even larger and emptier than the voids we see in the distribution of galaxies. The Euclid Space Telescope, launched by the European Space Agency in 2023, is currently mapping the distribution of dark matter across billions of light-years using weak gravitational lensing. Its preliminary results confirm what cosmologists have long suspected. The invisible universe is just as empty, just as void-dominated as the visible one. We're not just alone in the darkness. We're alone in an invisible darkness that dwarfs anything we can see. But the terror of cosmic emptiness goes deeper than just the vast distances and invisible matter. It's written into the fundamental laws of physics themselves. The cosmological constant, Einstein's mathematical description of the energy of empty space, has a value that makes the universe's fate inevitable. Empty space itself has energy, and this energy drives the accelerating expansion that will ultimately separate all matter into isolated islands of existence. Einstein originally introduced the cosmological constant to keep the universe static, then called it his greatest blunder when Edwin Hubble discovered that the universe was expanding. But modern observations have vindicated Einstein's original equation. The cosmological constant isn't zero. It has a small but positive value that ensures the universe will expand forever, becoming emptier and emptier with each passing eon. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, has detected ripples in space-time itself caused by colliding black holes and neutron stars. These gravitational waves travel through the emptiness of space at the speed of light, carrying information about some of the most violent events in the universe. But even these cosmic catastrophes, events that release more energy in gravitational waves than all the stars in the observable universe emit in light, barely disturb the vast emptiness through which they propagate. When two black holes collide and merge, they create gravitational waves that stretch and compress space itself. Yet these waves, detectable only by the most sensitive instruments ever built, represent tiny fluctuations in an otherwise perfectly empty space-time. The collision of objects containing dozens of times the mass of our Sun produces ripples so small they change the length of LIGO's 4-kilometer arms by less than 1/10,000th the width of a proton. This incredible sensitivity reveals something profound about the nature of space itself. Empty space isn't just the absence of matter. It's a dynamic medium that can be stretched, compressed, and made to vibrate. The Virgo detector in Italy and the Kagra detector in Japan have joined LIGO in creating a global network that monitors the emptiness of space for these tiny disturbances, confirming that even the vacuum of space has structure and properties. The quantum vacuum, studied in laboratories around the world, reveals that empty space is never truly empty. Virtual particles constantly pop into existence and annihilate each other in time frames so brief they don't violate conservation of energy. The Casimir effect, first measured in 1948, shows that these quantum fluctuations create measurable forces between closely spaced metal plates in vacuum. But here's what's truly unsettling. These quantum fluctuations should produce an enormous cosmological constant, one that would make the universe expand so rapidly that atoms themselves couldn't form. The fact that our universe exists at all requires the cosmological constant to be almost exactly zero, but not quite. It's fine-tuned to a precision of 1 part in 10 to the 120th power, a number so small it defies comprehension. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. Why is the energy of empty space just barely large enough to drive cosmic acceleration, but not so large that it prevents the formation of galaxies, stars, and life? Some physicists argue that we live in a multiverse where most universes have the wrong cosmological constant and remain empty forever, while we happen to exist in one of the rare universes where the value allows for complexity. The idea of eternal inflation, proposed by physicist Alan Guth and refined by Andre Linde and others, suggests that our observable universe is just one bubble in an infinite sea of expanding space. Most of this infinite multiverse consists of empty, inflating space that never develops the structure necessary for galaxies, stars, or life. We exist in a tiny pocket where inflation stopped and matter could condense, surrounded by infinite emptiness. The Cosmic Background Explorer, or COBE, satellite first detected the tiny temperature fluctuations in the cosmic microwave background that seeded all the structure we see today. These fluctuations, measured to be about 1 part in 100,000, represent the quantum fluctuations of the inflating universe stretched to cosmic scales. Without these primordial ripples, the universe would have remained perfectly smooth and empty forever. But even with these fluctuations, most of the universe remains empty. The Sloan Digital Sky Survey's three-dimensional maps show that galaxies occupy less than 1% of the universe's volume. The rest is cosmic voids, regions where the density of matter is less than 10% of the cosmic average. Some of these voids are so empty that if Earth were placed at their center, the nearest galaxy would be over 1 billion light-years away. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, stretches across 10 billion light-years, about 7% of the diameter of the observable universe. Yet even this enormous structure is mostly empty space, with galaxies strung along filaments like lights on a cosmic Christmas tree. The spaces between the filaments contain almost nothing. No galaxies, no stars, no planets, just the occasional hydrogen atom drifting through the darkness. Recent observations from the Dark Energy Survey have mapped the distribution of matter across 1/8 of the entire sky, revealing the cosmic web in unprecedented detail. These maps confirm that the universe's structure resembles a vast foam, with dense filaments surrounding enormous empty bubbles. The bubbles, the cosmic voids, contain 95% of the universe's volume, but less than 5% of its matter. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will survey hundreds of millions of galaxies to map dark energy's effects with even greater precision. Its observations will help determine whether dark energy is truly constant or whether it's changing over time. If dark energy is increasing, the universe's expansion will accelerate even faster, making the future emptiness even more profound. But perhaps the most terrifying aspect of cosmic emptiness is how it affects our understanding of life itself. The Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy. Even optimistic estimates suggest that technological civilizations are separated by hundreds or thousands of light-years, distances so vast that communication would take millennia. The Fermi paradox asks why, in a galaxy containing hundreds of billions of stars, we haven't detected any signs of advanced civilizations. One possible answer is that the universe is simply too empty, too vast, for civilizations to find each other. We might be like isolated islands in an infinite ocean, each developing independently, never knowing that others exist. The search for extraterrestrial intelligence, or SETI, has monitored millions of stars for artificial radio signals without detecting any clear evidence of alien technology. The breakthrough. Listen Project, funded by Russian billionaire Yuri Milner, is conducting the most comprehensive search ever undertaken, monitoring billions of stars across multiple wavelengths. So far, the results confirm what the emptiness of space suggests. We appear to be alone. The Kepler Space Telescope discovered thousands of exoplanets before its mission ended in 2018, confirming that planets are common throughout the galaxy. The Transiting Exoplanet Survey Satellite, or TESS, continues this work, finding potentially habitable worlds around nearby stars. Yet despite the abundance of planets, the universe remains silent. The emptiness extends beyond just matter and energy. It may include the absence of other minds, other civilizations, other forms of consciousness. The silence from space becomes even more haunting when you consider the age of the universe. At 13.8 billion years old, the cosmos has had plenty of time for civilizations to arise, develop technology, and spread across the galaxy. Yet the Arecibo Observatory, before its collapse in 2020, and the Green Bank Telescope continue to detect nothing but natural radio emissions from pulsars, quasars, and other cosmic phenomena. The emptiness isn't just physical, it appears to be biological and technological as well. This cosmic loneliness is amplified by what astronomers call the Great Filter, a hypothetical evolutionary bottleneck that prevents most life from developing into spacefaring civilizations. The filter could be behind us, meaning we're incredibly lucky to have evolved intelligence, or it could be ahead of us, suggesting that something catastrophic awaits all technological species. Either way, the vast emptiness of space provides no comfort, no evidence of others who have successfully navigated the challenges of existence. The James Webb Space Telescope has begun analyzing the atmospheres of exoplanets, searching for biosignatures, chemical signs of life, like oxygen, methane, or industrial pollutants. Its infrared vision can detect these molecules in the atmospheres of planets orbiting nearby stars. But so far, the results show worlds that are either too hot, too cold, or chemically sterile. The universe appears to be not just empty of matter, but empty of life. Even more disturbing is the realization that this emptiness is accelerating. The Hubble Space Telescope's observations of distant supernovae revealed that galaxies are moving away from us faster now than they were in the past. This acceleration means that the observable universe, the sphere of space from which light has had time to reach us, is actually shrinking in terms of the number of galaxies we can see. Right now, we can observe about 2 trillion galaxies in the observable universe. But as cosmic expansion accelerates, galaxies beyond a certain distance will recede so fast that their light will never reach us. In about 150 billion years, all galaxies outside our local group will have disappeared beyond our cosmic horizon. Future astronomers will see a universe containing only a few dozen galaxies, surrounded by infinite darkness. The cosmic microwave background radiation, currently detectable as a faint glow filling all of space, will also fade away. This radiation, the afterglow of the Big Bang, is already stretched to microwave wavelengths by cosmic expansion. As space continues to expand, these microwaves will be stretched to radio waves, then to wavelengths longer than the size of galaxies themselves, becoming effectively undetectable. Future civilizations will have no evidence that the Big Bang ever occurred. They'll see a static universe containing only their local group of galaxies, with no way of knowing that billions of other galaxies once existed. The cosmic microwave background, one of the strongest pieces of evidence for the Big Bang theory, will have been erased by the very expansion it helped us discover. The Planck satellite's final data release in 2018 provided the most precise measurements ever made of the cosmic microwave background. These observations confirm that the universe is geometrically flat, meaning it will expand forever. There's no possibility of a big crunch where gravity eventually overcomes expansion and pulls everything back together. The universe is destined for maximum entropy, a state of perfect, cold, empty equilibrium. This heat death of the universe, first proposed by physicist Rudolf Clausius in 1865, represents the ultimate triumph of emptiness over structure. As the universe expands and cools, all energy will eventually be distributed evenly throughout space. Stars will burn out, black holes will evaporate through Hawking radiation, and even protons may decay, leaving nothing but a thin soup of elementary particles in an infinite void. The timescales involved are almost incomprehensible. The last stars will burn out in about 100 trillion years. Black holes will evaporate over periods ranging from 10 to the 64th power years for stellar mass black holes to 10 to the 100th power years for supermassive black holes. If protons decay, as some theories suggest, even atomic nuclei will disappear after 10 to the 34th power years. These numbers are so large they lose all meaning. 10 to the 100th power years is longer than the current age of the universe, by a factor larger than the number of atoms in the observable universe. We're talking about a future so distant that the entire history of stars, galaxies, and life represents just the first fleeting moment of cosmic time. But the emptiness we observe today gives us a preview of this ultimate fate. The cosmic voids, those enormous empty regions between galaxy filaments, show us what the entire universe will eventually become. The Boötes Void, 330 million light-years across and containing almost no galaxies, is a glimpse of the universe's future, infinite, cold, and empty. The large-scale structure surveys conducted by teams around the world have mapped these voids in detail, revealing their internal structure. Even the emptiest voids aren't perfectly uniform. They contain subtle variations in density that trace back to quantum fluctuations in the early universe. These tiny ripples in nothingness are all that remains of the primordial chaos from which everything emerged. The Cosmic Evolution Survey, conducted with the Hubble Space Telescope, has tracked how cosmic voids have grown over time. By observing galaxies at different distances, and therefore different ages, astronomers can see how the cosmic web has evolved. The results show that voids have been growing steadily larger and emptier throughout cosmic history, and this growth is accelerating. Dark energy, the mysterious force driving cosmic acceleration, appears to be a property of space itself. As space expands, more dark energy is created, making the expansion accelerate even faster. It's a runaway process with no known mechanism to stop it. The more empty space the universe creates, the faster it creates even more empty space. The Vera Rubin Observatory, currently under construction in Chile, will conduct the legacy survey of space and time, mapping billions of galaxies and measuring dark energy's effects with unprecedented precision. Its observations will help determine whether dark energy is truly constant or whether it's evolving over time. But all current evidence suggests that dark energy will continue to drive the universe toward ever greater emptiness. Recent theoretical work by physicists like Sean Carroll and others has explored the possibility that our universe is just one phase in an eternal cycle of expansion and contraction. But even these cyclic models require the universe to become essentially empty between cycles, with all structure dissolved into a featureless void before the next cycle begins. The anthropic principle suggests that we observe a universe compatible with our existence simply because we exist to observe it. Universes that are too empty or too dense for life to evolve have no observers to notice their properties. But this principle offers cold comfort when we realize that our universe is becoming emptier with each passing moment, moving inexorably toward a state incompatible with any form of life or consciousness. The fine-tuning required for a universe that can support complexity is extraordinary. If dark energy were just slightly stronger, galaxies would never have formed. If it were slightly weaker, the universe would have collapsed before stars could evolve. We exist in a narrow window of cosmic parameters that allows for structure, complexity, and consciousness. A window that is slowly closing as the universe expands and empties. The window of cosmic habitability isn't just closing, it's slamming shut with mathematical precision. The illustrious simulation, one of the most comprehensive computer models of cosmic evolution ever created, shows exactly how this process unfolds. Starting from the conditions observed in the cosmic microwave background, the simulation follows the universe's evolution for 13.8 billion years, revealing how galaxies form, merge, and eventually become isolated in an expanding void. What makes these simulations truly chilling is their accuracy. When astronomers compare the illustrious results to actual observations from telescopes like Hubble and the Very Large Telescope, the match is nearly perfect. The simulation correctly predicts the number of galaxies we observe, their sizes, their colors, and even the distribution of elements within them. This isn't speculation, it's a precise mathematical description of how emptiness conquers structure. The Eagle simulation, conducted by an international team of researchers, focuses specifically on galaxy formation and confirms the same terrifying trend. As cosmic time progresses, star formation rates decline, Galaxies merge into larger but fewer systems, and the spaces between them grow ever larger. The simulation shows that we're living during the universe's brief golden age of complexity, a fleeting moment between the chaos of the early universe and the eternal emptiness of the far future. But perhaps the most disturbing aspect of cosmic emptiness is how it affects the very atoms that make up your body. The protons in your cells, the neutrons in your DNA, the electrons that enable your thoughts, all of these particles may be fundamentally unstable over cosmic timescales. Grand unified theories in physics predict that protons should decay with a half-life of about 10 to the 34th power years. This means that even if the universe somehow avoided heat death, even if dark energy mysteriously stopped accelerating expansion, the very matter that makes up stars, planets, and life would eventually disintegrate. The Super Kamiokande detector in Japan and the IceCube Neutrino Observatory at the South Pole have searched for evidence of proton decay without success, but the predicted lifetimes are so long that we wouldn't expect to see it happening yet. If protons do decay, the implications are staggering. Every atom in your body, every molecule in every living thing, every rock on every planet around every star will eventually dissolve into a thin gas of leptons and photons. The universe won't just become empty of galaxies and stars, it will become empty of matter itself, leaving only massless particles drifting through infinite space. The Homestake experiment, deep underground in South Dakota, and its successor experiments have detected neutrinos from the Sun, confirming that these nearly massless particles can travel through the entire Earth without interacting with a single atom. In a universe where protons have decayed, neutrinos and photons might be the only remnants of what was once a cosmos filled with complexity and life. Even black holes, those seemingly eternal gravitational monsters, are not immune to the universe's drive toward emptiness. Stephen Hawking's theoretical work in the 1970s showed that black holes emit radiation and slowly evaporate. The smaller the black hole, the faster it evaporates. Stellar mass black holes will take about 10 to the 64th power years to completely disappear, while supermassive black holes like the one at the center of our galaxy will persist for 10 to the 100th power years. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will detect gravitational waves from merging supermassive black holes across cosmic distances. These observations will help us understand how black holes grow and merge, but they also remind us that even these cosmic giants are temporary features in a universe trending toward absolute emptiness. When the last black hole finally evaporates in the unimaginably distant future, it will leave behind only a sparse collection of elementary particles, electrons, positrons, neutrinos, and photons, drifting through space at temperatures just barely above absolute zero. The universe will have achieved maximum entropy, a state of perfect equilibrium where no energy can be extracted to do work, create structure, or support life. But the terror of cosmic emptiness isn't just about the far future. It's about what this emptiness reveals about the nature of existence itself. The fact that our universe is fine-tuned for complexity suggests that most possible universes are empty, sterile voids where nothing interesting ever happens. We may be living in an extraordinarily rare pocket of reality where the laws of physics allow for stars, planets, and consciousness. The string theory landscape, proposed by physicists like Leonard Susskind, suggests that there may be 10 to the 500th power different possible universes, each with different values for fundamental constants like the strength of gravity, the mass of electrons, or the cosmological constant. In the vast majority of these universes, the parameters are wrong for complexity. They're either too empty or too dense, too hot or too cold, expanding too fast or collapsing too quickly. If this multiverse theory is correct, then emptiness is the default state of reality. Universes like ours, where matter can clump together to form galaxies, stars, and planets, are incredibly rare exceptions in an infinite sea of sterile possibilities. We exist in a tiny bubble of complexity surrounded by infinite emptiness, not just in space, but in the space of all possible realities. The cosmic microwave background radiation carries within it the seeds of this terrifying realization. The Planck satellite's measurements show that the early universe was incredibly smooth, with density variations of only 1 part in 100,000. These tiny fluctuations, amplified by cosmic inflation, grew into all the structure we see today. But they also reveal how close the universe came to remaining perfectly smooth and empty forever. If the primordial fluctuations had been just slightly smaller, gravity would never have been able to overcome cosmic expansion to form the first stars and galaxies. If they had been slightly larger, the universe would have collapsed into black holes before complex chemistry could develop. We exist because the universe hit an incredibly narrow target in the space of possible initial conditions. The Cosmic Background Imager and the Degree Angular Scale Interferometer have measured these fluctuations with extraordinary precision, confirming that we live in a universe balanced on a knife's edge between eternal emptiness and immediate collapse. The fact that we're here to make these measurements is itself a kind of cosmic miracle, a temporary victory of complexity over the universe's natural tendency toward emptiness. But this victory is temporary. The Dark Energy Survey has mapped the distribution of matter across billions of light-years, showing how cosmic structure is already beginning to dissolve. Galaxy clusters are being pulled apart by dark energy, their member galaxies scattered into the growing voids. The cosmic web that connects all matter is slowly unraveling, leaving isolated islands of complexity in an ocean of nothingness. The Euclid mission will map this dissolution in real time, tracking how dark energy tears apart the largest structures in the universe. Its observations will show us exactly how fast the cosmic web is dissolving, and how long we have before our own local group becomes completely isolated from the rest of the cosmos. Recent observations from the Chandra X-ray Observatory have detected hot gas being stripped from galaxy clusters as they're pulled apart by cosmic expansion. This gas, heated to millions of degrees by the cluster's gravity, is being dispersed into the cosmic voids where it will cool and fade into invisibility. We're watching the universe's matter being redistributed from dense, interesting regions into empty, featureless space. The process is irreversible. Once matter falls into a cosmic void, it becomes so dilute that gravity can never pull it back together. The voids act like cosmic sinks, draining matter and energy from the structured regions of the universe. As time passes, more and more matter falls into these voids, making them larger and emptier, while the remaining structures become smaller and more isolated. The mathematics of this cosmic dissolution are as precise as they are terrifying. The Lambda CDM model, our best description of the universe's composition and evolution, predicts exactly how this emptiness will unfold. Lambda represents dark energy. CDM stands for cold, dark matter, and together they describe a universe where emptiness isn't just inevitable. It's accelerating according to well-understood physical laws. The Supernova Cosmology Project's measurements of distant Type Ia supernovae revealed that this acceleration began about 5 billion years ago, roughly when our solar system was forming. Before that, the universe's expansion was actually slowing down as gravity fought against the initial impulse of the Big Bang. But once the universe expanded enough for dark energy to dominate over matter, acceleration became inevitable and irreversible. This timing isn't coincidental. Computer simulations show that dark energy begins to dominate precisely when the universe has expanded enough for matter density to drop below a critical threshold. It's as if the universe has a built-in timer, counting down to the moment when emptiness takes control. We're living in the brief transition period between a matter-dominated cosmos and a dark energy-dominated void. The Baryon Oscillation Spectroscopic Survey, part of the Sloan Digital Sky Survey, has mapped the positions of over 1 million galaxies to trace how this transition occurred. By measuring the clustering patterns of galaxies at different distances, and therefore different times in cosmic history, astronomers can see exactly when dark energy began to tear apart the cosmic web. These observations reveal something deeply unsettling. The universe's structure formation peaked about 10 billion years ago and has been declining ever since. The rate at which new stars form has dropped by a factor of 10 since the cosmic noon era. Galaxy mergers, which once built larger and more complex systems, are becoming rarer as cosmic expansion pulls potential merger partners beyond each other's gravitational reach. The Hubble Space Telescope's Cosmic Evolution Survey has documented this decline in exquisite detail. By observing galaxies at different redshifts, different look-back times, astronomers can construct a timeline of cosmic activity. The results show that we're living in a universe past its prime, a cosmos that has already begun its long slide toward emptiness and death. But the most chilling aspect of this cosmic decline is how it affects the possibility of life elsewhere in the universe. The habitable zone around stars, the region where liquid water can exist on planetary surfaces, is shrinking as stellar evolution progresses. Main-sequence stars like our Sun will eventually exhaust their hydrogen fuel and expand into red giants, sterilizing any planets in their vicinity. The Kepler Space Telescope's observations of stellar variability show that even stable stars like our Sun undergo long-term changes that affect their habitable zones. Solar luminosity increases by about 1% every 100 million years, meaning that Earth will become uninhabitable due to a runaway greenhouse effect in about 1 billion years, long before the Sun exhausts its fuel. For life to persist in the universe, it would need to migrate to planets around smaller, longer-lived stars. Red dwarf stars can burn for trillions of years, potentially providing stable energy sources long after stars like our Sun have died. But the TRAPPIST-1 system and other red dwarf planetary systems studied by the James Webb Space Telescope show that these stars are prone to violent flares that could strip away planetary atmospheres. The combination of stellar evolution, cosmic expansion, and the eventual heat death of the universe creates a narrow window of time during which complex life can exist. We may be living during the universe's brief biological epoch, a fleeting moment between the sterile early cosmos and the empty far future when conditions allow for the chemistry of life. The Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy, becomes even more pessimistic when you factor in these cosmic constraints. Not only must life evolve intelligence and technology, but it must do so during the narrow window when the universe supports complexity. Most of cosmic time, both past and future, is hostile to life. The Fermi paradox takes on new meaning in this context. Perhaps we don't detect other civilizations not because they don't exist, but because the universe's window of habitability is so narrow that most potential civilizations arise either too early, when heavy elements are scarce, or too late, when cosmic expansion has isolated star systems beyond the reach of interstellar communication. Recent studies of globular clusters, some of the oldest stellar systems in our galaxy, suggest that planets in these ancient environments lack the heavy elements necessary for rocky planet formation and complex chemistry. The first generations of stars produced only hydrogen and helium. It took billions of years of stellar nucleosynthesis to create the carbon, oxygen, and iron that make life possible. Conversely, future generations of stars will form in an increasingly metal-rich but increasingly isolated universe. As cosmic expansion continues, the raw materials for star formation, hydrogen and helium gas, will be spread so thin that new star formation will essentially cease. The universe will enter what astronomers call the degenerate era, when only the longest-lived red dwarf stars continue to shine. The timeline for this cosmic sterilization is well established. Star formation will peak in about 1 trillion years, then decline exponentially as the universe runs out of gas. The last stars will form in about 100 trillion years, after which the universe will be populated only by stellar remnants, white dwarfs, neutron stars, and black holes, slowly cooling in the darkness. But even these remnants are temporary. White dwarf stars, the cooling cores of dead sun-like stars, will fade to invisibility over hundreds of trillions of years. Neutron stars, the collapsed cores of massive stars will slowly lose energy through magnetic braking and gravitational wave emission. Only black holes will persist, and even they will eventually evaporate through Hawking radiation. The Event Horizon Telescope's observations of the supermassive black hole in galaxy M87 provide a glimpse of these cosmic endpoints. This black hole, containing 6.5 billion times the mass of our Sun, will outlast every star in its galaxy, every planet, every trace of the civilization that once surrounded it. Yet even this cosmic giant will eventually evaporate, leaving nothing but elementary particles in an infinite void. The timescales involved in black hole evaporation are almost incomprehensible. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely. The supermassive black hole at the center of our galaxy, with a mass of 4 million suns, will persist for 10 to the 99th power years. These numbers are so large that they make the current age of the universe, 13.8 billion years, seem like an instant. Yet even these vast timescales are finite. Eventually every black hole will evaporate, every particle will decay, and the universe will reach a state of maximum entropy where no further change is possible. The second law of thermodynamics, which governs the flow of energy from hot to cold, ensures that the universe will eventually reach thermal equilibrium, a state of perfect, cold, empty uniformity. This heat death represents the ultimate triumph of emptiness over structure, of chaos over order, of meaninglessness over complexity. It's not just the end of life or consciousness, it's the end of the possibility that anything interesting could ever happen again. The universe will have exhausted its capacity for surprise, for beauty, for meaning. The cosmic microwave background radiation, currently at a temperature of 2.7 Kelvin, will continue to cool as the universe expands. In the far future, this radiation will be so cold and so dilute that it will be indistinguishable from the quantum vacuum fluctuations that permeate empty space. The last echo of the Big Bang will fade into silence. But here's where the story takes an even more disturbing turn. The emptiness we observe isn't just a consequence of cosmic evolution, it may be a fundamental feature of reality itself. Quantum field theory, our best description of how particles and forces work at the smallest scales, reveals that even the vacuum of space is seething with activity. Virtual particles constantly pop into existence and annihilate each other in time frames so brief they don't violate conservation of energy. The Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and confirmed by numerous experiments, shows that this quantum vacuum has measurable consequences. When two metal plates are placed very close together in a vacuum, the quantum fluctuations between them are restricted compared to the fluctuations outside. This creates a tiny but measurable force that pushes the plates together, proving that empty space isn't truly empty. But here's the terrifying part. Calculations of the vacuum energy density based on quantum field theory give a result that's larger than the observed cosmological constant by a factor of 10 to the 120th power. This is called the cosmological constant problem, and it represents the largest discrepancy between theory and observation in all of physics. The vacuum energy should be so large that it would prevent the formation of atoms, let alone galaxies and stars. The fact that our universe exists at all requires the vacuum energy to be almost exactly zero, but not quite. It's fine-tuned to a precision that defies comprehension, like balancing a pencil on its point for billions of years while earthquakes shake the ground. This fine-tuning suggests that most possible universes are dominated by vacuum energy and remain empty forever, unable to support any form of structure or complexity. String theory attempts to solve this problem by proposing that our universe is just one of countless possibilities in a vast landscape of potential realities. In this multiverse, most universes have the wrong vacuum energy and remain sterile voids. We exist in one of the incredibly rare universes where the vacuum energy is just right for complexity, surrounded by infinite emptiness in the space of all possible realities. The Large Hadron Collider at CERN has searched for evidence of extra dimensions and supersymmetric particles that might explain this fine-tuning, but so far has found nothing beyond the standard model of particle physics. The absence of new physics at accessible energy scales suggests that the solution to the cosmological constant problem, if it exists, lies far beyond our current experimental reach. Meanwhile, the Planck satellite's measurements of the cosmic microwave background have confirmed the cosmological constant's value to unprecedented precision. The observations show that dark energy makes up exactly 68.3% of the universe's energy density, with an uncertainty of less than 1%. We know exactly how much vacuum energy exists, but we have no idea why it has this particular value rather than being vastly larger or exactly zero. This precision is both a triumph and a curse. We can measure the universe's emptiness with extraordinary accuracy, but we can't explain why it's not infinitely emptier or infinitely denser. The universe appears to be balanced on a knife's edge between two forms of nothingness: the sterile void of excessive vacuum energy and the collapsed singularity of insufficient vacuum energy. Recent observations from the Dark Energy Survey and the Euclid mission are testing whether dark energy is truly constant or whether it's evolving over time. If dark energy is increasing, as some theoretical models suggest, the universe's expansion will accelerate even faster, making the future emptiness even more profound. If it's decreasing, there's a slim possibility that cosmic expansion could eventually slow down or even reverse. But all current evidence suggests that dark energy is indeed constant, a fundamental property of space itself that ensures the universe will expand forever. The Vera Rubin Observatory's Legacy Survey of Space and Time will provide the most precise measurements of dark energy ever made, but astronomers expect these observations to confirm what we already know: the universe is destined for eternal emptiness. The philosophical implications of this cosmic emptiness are staggering. If consciousness is a temporary arrangement of matter and energy that emerges briefly in certain complex systems, then the universe's drive toward maximum entropy means that consciousness itself is doomed. Not just human consciousness, but any form of awareness that might arise anywhere in the cosmos. The anthropic principle offers one way to think about this predicament. We observe a universe compatible with our existence because we exist to observe it. Universes that are too empty or too dense for consciousness to evolve have no observers to notice their properties. But this principle provides cold comfort when we realize that our universe is moving inexorably toward a state incompatible with any form of awareness. Some physicists have proposed that advanced civilizations might find ways to survive the heat death of the universe by slowing down their metabolic processes as the cosmos cools. Freeman Dyson's eternal intelligence hypothesis suggests that conscious beings could potentially persist forever by using exponentially less energy as the universe approaches absolute zero temperature. But even these optimistic scenarios require the universe to cool gradually, rather than undergo phase transitions that could destroy all structure instantaneously. Recent theoretical work on vacuum metastability suggests that our current vacuum state might not be the lowest possible energy state. If the universe undergoes a vacuum decay event, a bubble of true vacuum could expand at the speed of light, annihilating everything in its path. The discovery of the Higgs boson at the Large Hadron Collider in 2012 allowed physicists to calculate the stability of our current vacuum state. The results are unsettling. Our vacuum appears to be metastable, meaning it's stable for now, but could potentially decay into a lower energy state. The timescale for such decay is longer than the current age of the universe, but it's not infinite. If vacuum decay occurs, it would represent the ultimate form of cosmic emptiness, not just the absence of matter and energy, but the destruction of the very laws of physics that allow for existence. The expanding bubble of true vacuum would rewrite the fundamental constants of nature, making atoms impossible and erasing all traces of the complexity that once existed. The cosmic microwave background radiation carries subtle signatures that could reveal whether our universe has already experienced partial vacuum decay events in the past. The Planck satellite's observations show no evidence of such events, but future missions with even greater sensitivity might detect the scars of ancient phase transitions. Even without vacuum decay, the universe's expansion toward infinite emptiness raises profound questions about the meaning and purpose of existence. If everything we build, everything we discover, everything we love is destined to be erased by cosmic expansion and entropy, what significance can our lives possibly have? Yet perhaps there's a different way to think about cosmic emptiness. The fact that we exist at all in a universe so finely tuned for nothingness is itself remarkable. We are the universe becoming aware of itself, matter organized into patterns complex enough to contemplate their own existence. In a cosmos trending toward maximum entropy, consciousness represents a temporary but magnificent victory of order over chaos. The atoms in your body were forged in the nuclear furnaces of ancient stars that lived and died billions of years ago. The carbon in your DNA, the oxygen you breathe, the iron in your blood, all were created in stellar cores and dispersed by supernova explosions across the galaxy. You are quite literally made of stardust, a temporary arrangement of cosmic material that has somehow learned to think and feel and wonder. This perspective transforms the terror of cosmic emptiness into something approaching awe. Yes, the universe is vast and empty and destined for heat death. But in this tiny corner of space and time, matter has organized itself into galaxies, stars, planets, and life. Against all odds, in defiance of entropy, complexity has emerged from simplicity, consciousness from unconsciousness, meaning from meaninglessness. The emergence of consciousness in an overwhelmingly empty universe represents something so improbable that it borders on the miraculous. Consider the chain of events that had to unfold perfectly for you to exist. The Big Bang had to produce exactly the right amount of matter and energy. The fundamental forces had to have precisely the right strengths. The first stars had to form and die to create heavy elements. Our solar system had to condense in just the right location in the galaxy. Earth had to maintain liquid water for billions of years, and evolution had to navigate countless contingencies to produce intelligent life. Each step in this process was extraordinarily unlikely. The rare Earth hypothesis, proposed by paleontologist Peter Ward and astronomer Donald Brownlee, argues that complex life requires such a specific set of conditions that it may be exceedingly uncommon in the universe. Earth's large moon stabilizes our planet's rotation. Jupiter's gravity shields us from asteroid impacts. Our location in the galaxy protects us from radiation, and dozens of other factors had to align perfectly. The Gaia hypothesis, developed by James Lovelock, suggests that Earth's biosphere actively maintains the conditions necessary for life through complex feedback mechanisms. The planet's temperature, atmospheric composition, and ocean chemistry are regulated by living systems in ways that keep Earth habitable despite changes in solar luminosity and other external factors. We exist because life itself has learned to fight against entropy and maintain order. But this biological order is temporary and fragile. The Permian-Triassic extinction event, which occurred 252 million years ago, eliminated 96% of marine species and 70% of terrestrial species. The Chicxulub impact that ended the age of dinosaurs 66 million years ago shows how quickly cosmic events can reset the evolutionary clock. Life on Earth has survived multiple near extinctions, but each event reminds us how precarious our existence really is. The Kepler Space Telescope's discovery of thousands of exoplanets has revealed that Earth-like worlds may be more common than previously thought, but it has also shown how many ways planetary systems can go wrong. Hot Jupiters migrate inward and destroy terrestrial planets, stellar flares strip away atmospheres, and tidal forces lock planets in configurations that prevent the development of complex chemistry. Even if life does arise elsewhere, the vast distances between stars ensure that most civilizations will remain forever isolated. The nearest potentially habitable exoplanet, Proxima Centauri b, is over 4 light-years away. At the speeds achievable with current technology, a journey there would take tens of thousands of years. The universe's emptiness doesn't just separate matter, it separates minds, ensuring that most conscious beings will live and die without ever knowing that others exist. The search for extraterrestrial intelligence has monitored millions of stars for artificial signals without detecting any clear evidence of alien technology. The Breakthrough Listen project, using some of the world's most sensitive radio telescopes, has found nothing but natural cosmic noise. The silence is deafening, suggesting that either technological civilizations are incredibly rare or they don't last long enough to make their presence known across interstellar distances. This cosmic loneliness is amplified by the realization that even if other civilizations exist, we may never be able to communicate with them meaningfully. The time delays involved in interstellar communication are measured in years or decades, making real-time conversation impossible. By the time we receive a message from another star system, the civilization that sent it may have evolved beyond recognition or gone extinct entirely. The Fermi paradox becomes even more haunting when viewed against the backdrop of cosmic emptiness. In a galaxy containing hundreds of billions of stars, where are all the aliens? One possibility is that the Great Filter, some evolutionary bottleneck that prevents most life from developing into spacefaring civilizations, lies ahead of us rather than behind us. Perhaps every technological species eventually destroys itself or is destroyed by cosmic forces before it can spread beyond its home system. Climate change, nuclear weapons, artificial intelligence, biotechnology, asteroid impacts – there are numerous ways that advanced civilizations could face extinction. The universe's emptiness may be filled with the ghosts of dead civilizations, species that briefly achieved consciousness and technology before succumbing to internal conflicts or external catastrophes. But even if some civilizations survive these challenges, they face the ultimate enemy, time itself. The universe's accelerating expansion means that eventually, all galaxies outside our local group will recede beyond our cosmic horizon. Future civilizations will see a universe containing only a few dozen galaxies, with no evidence that billions of others once existed. They'll have no way of knowing about the rich cosmic history that preceded them. The cosmic microwave background radiation, currently our best evidence for the Big Bang, will fade away as the universe expands and cools. Future astronomers will see a static universe with no evidence of its dynamic past. The very observations that led us to understand cosmic evolution will become impossible, leaving future civilizations with no way to comprehend their cosmic context. This erasure of cosmic history represents a form of existential horror that goes beyond mere physical destruction. It's not just that civilizations will die, it's that all evidence of their existence will be erased by the universe's expansion. The cosmos will forget that complexity ever existed, that consciousness ever arose, that meaning was ever possible. The James Webb Space Telescope's observations of the most distant galaxies show us the universe as it was over 13 billion years ago, when it was young and dense and full of star formation. These ancient galaxies appear surprisingly mature and massive, suggesting that structure formation happened faster than our models predicted. But they also remind us that we're seeing the universe's youth, a time when cosmic evolution was rapid and dramatic. Today's universe is middle-aged and slowing down. Star formation rates have declined by a factor of 10 since the cosmic noon era. Galaxy mergers are becoming rarer as cosmic expansion pulls potential partners beyond each other's gravitational reach. We're living in a universe past its prime, a cosmos that has already begun its long slide toward emptiness and death. The local group of galaxies, our cosmic neighborhood containing the Milky Way, Andromeda, and about 50 smaller galaxies, will eventually merge into a single massive galaxy. Computer simulations show this process unfolding over the next few billion years, with our galaxy and Andromeda colliding and merging while the smaller galaxies are either absorbed or ejected into intergalactic space. This future galaxy, sometimes called Milkomeda, will be an island of complexity in an increasingly empty universe. As cosmic expansion accelerates, all other galaxies will recede beyond our horizon, leaving Milkomeda alone in an infinite void. Future civilizations in this merged galaxy will see a universe containing only their own stars, with no evidence that other galaxies ever existed. The psychological impact of such cosmic isolation is difficult to imagine. How would it feel to know that you're living in the only visible galaxy in an otherwise empty universe? Would such civilizations develop different philosophies, different religions, different ways of understanding their place in existence? Or would they simply accept their isolation as the natural state of things, never knowing what they had lost? Recent observations from the Dark Energy Survey have mapped the cosmic web in unprecedented detail, showing how matter is distributed along filaments separated by enormous voids. These maps reveal that the universe already resembles a vast foam, with dense regions containing galaxies surrounded by empty bubbles containing almost nothing. As cosmic expansion continues, the bubbles will grow larger while the filaments become thinner and more fragmented. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, stretches across 10 billion light-years. Yet even this enormous structure is mostly empty space, with galaxies strung along filaments like lights on a cosmic Christmas tree. The spaces between the filaments contain virtually nothing. No galaxies, no stars, no planets, just the occasional hydrogen atom drifting through the darkness. These cosmic voids aren't just empty, they're actively growing emptier. As the universe expands, matter falls into the voids where it becomes so dilute that gravity can never pull it back together. The voids act like cosmic drains, removing matter from the structured regions of the universe and dispersing it into featureless emptiness. The process of cosmic emptying is irreversible and accelerating. Once matter falls into a cosmic void, it becomes so dispersed that it can never again participate in the formation of stars, planets, or life. The universe is essentially mining its own complexity, extracting order from structured regions and dissolving it into the growing ocean of nothingness that dominates space. This dissolution isn't just theoretical, we can observe it happening in real time. The Chandra X-ray Observatory has detected hot gas being stripped from galaxy clusters as they're pulled apart by cosmic expansion. This gas, heated to millions of degrees by the cluster's gravity, is being dispersed into cosmic voids where it will cool and fade into invisibility. We're watching the universe's matter being redistributed from dense, interesting regions into empty, featureless space. The Atacama Large Millimeter Array, or ALMA, has observed similar processes on smaller scales, detecting gas being stripped from individual galaxies as they fall through galaxy clusters. This ram pressure stripping removes the raw material for future star formation, effectively sterilizing galaxies and ensuring they'll produce no new stars, planets, or possibilities for life. But perhaps the most disturbing aspect of cosmic emptiness is how it reveals the fundamental loneliness of consciousness itself. Even if the universe were teeming with life, even if every star had planets and every planet had civilizations, the vast distances between them would ensure that most conscious beings live and die in isolation, never knowing that others exist. The speed of light, which seems impossibly fast by human standards, is actually painfully slow on cosmic scales. Light from the nearest star takes over 4 years to reach us. A radio message to the nearest potentially habitable exoplanet would take over 4 years to arrive, and another 4 years for a response to return. Real-time conversation across interstellar distances is impossible. Consciousness is trapped by the universe's own speed limit. This isolation becomes even more profound when you consider the expansion of space itself. Galaxies beyond a certain distance are receding from us faster than light can travel between them. We can see these galaxies because their light was emitted when they were closer, but we can never communicate with them. They exist in a region of space that is causally disconnected from our own. They might as well be in a different universe entirely. The cosmic event horizon, the boundary beyond which galaxies are receding faster than light, is currently about 16 billion light-years away. But as cosmic expansion accelerates, this horizon is actually shrinking. Galaxies that we can see today will eventually disappear beyond our horizon, their light stretched to wavelengths so long they become undetectable. The observable universe is contracting even as the actual universe expands. This creates a terrifying paradox. The more we learn about the universe, the less of it we can actually observe. Future astronomers will have access to more advanced telescopes and more sophisticated instruments, but they'll see fewer galaxies, less cosmic history, and less evidence of the universe's rich past. Knowledge and ignorance will increase simultaneously. The Vera Rubin Observatory's Legacy Survey of Space and Time will map billions of galaxies over the next decade, creating the most detailed picture of cosmic structure ever assembled. But this survey may represent the peak of our cosmic knowledge. Future surveys will see fewer galaxies, less structure, and less evidence of the universe's complexity, as cosmic expansion carries more and more matter beyond our observational reach. Even more disturbing is the realization that this process of cosmic forgetting is already well underway. The most distant galaxies we can observe are seen as they were over 13 billion years ago, when the universe was young and dense. But these galaxies have continued to evolve during the billions of years their light has taken to reach us. By the time we see them, they may have changed beyond recognition or ceased to exist entirely. We're not just observing the universe, we're observing its past, a cosmic fossil record that becomes increasingly incomplete as we look deeper into space and further back in time. The universe we see is a ghost of what once was, and even these ghosts are fading as cosmic expansion stretches their light beyond detectability. The James Webb Space Telescope has begun to observe galaxies so distant that we're seeing them as they were when the universe was less than 1 billion years old. These ancient galaxies appear surprisingly mature and massive, challenging our understanding of how quickly structure can form in the early cosmos. But they also remind us that we're seeing the universe's infancy, a time when cosmic evolution was rapid and dramatic. Today's universe is entering what cosmologists call the stelliferous era, the age of stars. This era began about 100 million years after the Big Bang, when the first stars ignited, and it will continue for about 100 trillion years until the last red dwarf stars burn out. We're living during the early part of this era, when star formation is still relatively common and the universe retains some of its primordial energy. But even within the stelliferous era, we're past the universe's peak. Star formation rates peaked about 10 billion years ago and have been declining ever since. The universe is already middle-aged, having consumed much of its raw material for making new stars. The cosmic star formation rate is now only about 3% of what it was at its peak. This decline in star formation means that the universe is producing fewer planets, fewer opportunities for life, and fewer chances for consciousness to arise. The window of cosmic habitability, the period during which conditions are right for complex life, may be narrower than we thought. We might be living during the universe's brief biological epoch, a fleeting moment when the cosmos supports the chemistry of life. The red dwarf stars that will dominate the far future can burn for trillions of years, potentially providing stable energy sources long after stars like our Sun have died. But observations of red dwarf systems by the TRAPPIST telescope and other instruments show that these stars are prone to violent flares that could strip away planetary atmospheres. The long-term habitability of red dwarf systems remains uncertain. As the universe ages and cools, even these long-lived stars will eventually burn out. The last star will die in about 100 trillion years, leaving behind a cosmos populated only by stellar remnants, white dwarfs, neutron stars, and black holes, slowly cooling in the darkness. The stelliferous era will end, and the universe will enter what cosmologists call the degenerate era. During the degenerate era, the only sources of energy will be the slow decay of protons and the gradual evaporation of black holes through Hawking radiation. If protons are indeed unstable, as some theories predict, even atomic nuclei will eventually disintegrate, leaving only a thin soup of leptons and photons in an infinite void. The timescales involved in these processes are almost incomprehensible. Proton decay, if it occurs, has a half-life of at least 10 to the 34th power years. Black hole evaporation takes even longer. A black hole with the mass of our Sun would take 10 to the 67th power years to evaporate completely. These numbers are so large that they make the current age of the universe seem like an instant, yet even these vast timescales are finite. Eventually, every proton will decay, every black hole will evaporate, and the universe will reach a state of maximum entropy where no further change is possible. The cosmos will have exhausted its capacity for surprise, for complexity, for meaning. This is the heat death of the universe, not a dramatic explosion, but a gradual fade to black. The second law of thermodynamics ensures that this fate is inevitable. Entropy always increases in isolated systems, and the universe as a whole is the ultimate isolated system. Energy flows from hot to cold, order gives way to disorder, and complexity dissolves into simplicity. The universe began in a state of low entropy and high energy, and it will end in a state of maximum entropy and minimum energy. This thermodynamic arrow of time gives the universe a direction, a narrative arc that leads inexorably from order to chaos, from meaning to meaninglessness, from something to nothing. We exist during the brief middle chapter of this cosmic story, when entropy is low enough to allow for stars, planets, and life, but high enough to ensure that our existence is temporary. Speaking of cosmic structures that challenge our understanding of scale and meaning, I actually explored one of the most mind-bending examples in my video about the biggest galaxy we've discovered. A structure so massive it's bigger than your imagination and forces us to reconsider what's possible in our universe. It's a must-watch.